Still hear me, correct?
Yep, we can hear you, Scott. Take it away.
All right, great. So, welcome everyone. Thank you for having me. I apologize that I was not able to be there in person, but just know I am a very enthusiastic Linux supporter. So, hey, I'm more than happy to contribute. Just to give everyone a little bit of background, I am Scott Tashakkor. I do several jobs here at NASA. The one that probably got me involved at this is mostly the Deputy Tech Fellow for software. So essentially, we have through engineering, the Office of the Chief Engineer is our technical authority for everything. And then they have certain areas where they have a technical fellows. Dr. Lori Prokop is the technical fellow, and I'm one of her deputies that supports her in all these type things. I also, for Marshall, I supplement our chief engineer's office as the software SME, so I provide software support and knowledge and technical authority for the center itself. I was asked to talk a bit about this group, or talk to this group about verification and validation of the OS for NASA. I mean, essentially, if we're going to start using a lot of the OS and a lot of these type systems for NASA and our missions, we're going to have to worry about a bit more of the safety presentation or the safety aspects and how we step through all the processes to make sure that NASA is comfortable and is able to work with everything. So to that end, I'm going to continue on. Just to give everyone a little bit of outline, I have a little bit of an introduction. We'll go through a little bit of 7150.2, which is NASA software engineering requirements. We'll talk a little bit about how NASA defines safety critical, and also some of the requirements that once it's now defined as safety critical, now we apply. We'll also talk about NASA's requirement, or why NASA's requirements apply in this space, because again, everyone's going to think different things to say, hey, DoD does stuff differently. And then kind of what else is needed. And that what else is needed, there's a few little miscellaneous type areas that I wanted to talk about. So I wanted to kind of include them, but I didn't want to leave them out because they have information all throughout. Now, just for sake of awareness, I'm going to talk about some of the needs that need to be fulfilled as I'm going through. So even though there's this outline and it doesn't have one that says do specifically this, we're going to have all of the information. So introduction, and we will go through this a little bit. So essentially what I'm talking about is NASA software engineering requirements. They're at an agency level. So any center, program, or project can levy more requirements on their own. It's going to depend on their risk tolerance and risk acceptance criteria. We have the different technical authorities. If it is a technical wise, the Office of the Chief Engineer will provide that technical authority. There's also the Office of Safety and Mission Assurance, which comes through and again kind of audits the processes. Declares if software is safety critical or not, goes through and does the hazard analysis, hazard reports. And then since NASA does a lot with humans, we have the Office of the Chief Health and Medical Office, which is responsible for the safety, or basically for the health and medical operations of everyone. So even though NASA is kind of doing those three things, we have those technical authorities to match it. We also have our Chief Information Officers, or OCIO. They are the ones that enable a lot of the ability to use this. So they're going to be the ones that analyze for security protocols and everything of that aspect. But again, we're going to have a different risk assessment or a risk acceptance. And so I know this is all about enabling Linux and safety applications. And so oftentimes you'll find NASA is more risk averse in the current paradigm or the current kind of thought process of some of the other areas. And so we're going to have to go through a lot of kind of hoops to bounce through and make sure that we have a lot of uncertainty kind of at least explainable. For this, I wanted to make sure that I was talking on the Linux kernel. I do talk about some GNU programs. GNU is very good and everything, but from my understanding, this is more about the kernel itself, and so I wanted to kind of focus on that and not going through, well, what about all these packages? I mean, there's hundreds of thousands of packages, and there's more being developed every day. So again, I want to do that. A lot of times now it's going to come down to what is the criticality of some of the systems and what the tools are. So not only are we going to have to go through the usage of it, it's how critical of it. If we're using Linux or some sort of operating system or system for, let's say, just some sort of supplemental type aspect, maybe it's a music player, maybe it's just a display, that's going to be less critical than the other aspects. Because again, if we're using Linux or some of these operating systems in a environmental control or life support system, that needs to work. We're going to have to go through and talk about how deterministic it is. What are the faults and failure criteria that goes through it? And again, some of this also comes down to the tools. What tooling are we using? Are we able to do it? Are we even able to put this in space? We oftentimes get questions for, as we're going from Moon to Mars or even to the Moon, are we going to be able to compile? Are we even going to allow the astronauts or crew to start to compile and change the software? Or is it one of these things of you're always going to have to go back to ground and say, hey, from this point, we have all of our ground simulations, we have to test it, go through all the patches, and then update it. There are specific needs of information spread throughout this discussion. As I was saying earlier, I'm not going to have a single section say do A, B, C to click through everything. It's going to be, hey, I'm spreading it throughout to say, as you're meeting these requirements, you will get through. And then in the end, I'm not going to talk about the human rating requirements. There are special ones that we have. I did not want to kind of go through that because, again, we need to get through the first steps. But a lot of those human rating requirements start to go into it's multiple things. We can't use, for instance, a single fault, or we have to have like confirmation when the crew tries to activate something that could disable some sort of feature or maybe lead to a hazard. So again, at that point, I was thinking that was out of scope for at least this discussion. I mean, feel free, we can talk about it a little bit offline, but I wanted to leave that out. So, but there are some human rating requirements. So, as I've kind of been talking about this a little bit, and I wanted to, again, kind of just basically make everyone sure of this and understanding, when I talk about software, I want to make sure that everyone knows software is not all the same. We have the flight software. We have the non-flight software. Those are not the same. You'll find instances where OCIO or some of the things that, let's say, the Linux Foundation goes through, or the Linux kernel, I mean, they will go through a lot of these things. There's a difference in quality in what we try and do. Our flight software is not our flight software. So when you start to think about, hey, can I patch a zero-day flaw? Well, that's one of those little areas of where you have to think about it. Because if you're sitting there on the launch pad or sitting there about to run a test, you do not want to try and patch something and then find out, well, it broke something else on the side. So again, you're going to have to go through because we're doing a lot of specialized embedded applications for this. Engineering software is different than our general purpose software. One of the areas that I know that we'll often look at is, hey, we're trying to sit here and do a bunch of calculations. Well, that's engineering software. It's not our general purpose sitting on the open internet, able to get pinged on by anyone that feels like it. So again, we're walking through that. As well as, again, our safety critical versus our non-safety critical. We don't want people to think that just because we're saying this is safety critical, that applies to everything, or maybe it's in a non-safety critical application. So I know oftentimes people will start to go and kind of argue this and say, well, in this case, again, it starts to work out. So I just want to reiterate and make sure everyone knows that when I'm starting to talk through this, we have these different levels and the different aspects to go through. And you will oftentimes get caught in these discussions, especially when you're doing these safety applications or even when we're at NASA, because you have those different areas to go through. So to, again, now kind of step back a bit and give everyone, these are the NASA software engineering requirements. I'm going to go through this in a few different ways because this is going to be basically the majority of the discussion, and kind of going through and saying, hey, what is our safety applications, and how do we make sure that we've met all of the requirements that NASA needs? Because again, you'll start to look at, let's say the FAA, we have similarities between it. You'll also have the DoD or some of these other things, because one of the areas that NASA does work with is humans, and we have our astronauts in there. We have a different set of the humans requirements, and we define our software differently. We will let you take more chances when it is a CubeSat and it's just sitting in low Earth orbit, it's not hurt anyone, versus this is what is being used to run your actual vehicle and kind of control everything. So to give a background and to make sure that people are aware of this, we basically have the NASA-wide software classification structure. We base this based on the usage of the software with or within the NASA system. So even if it's coming from a off-the-shelf provider, we kind of go through this. We also look at the criticality of the system to NASA's major programs and projects. For instance, JWST, or James Webb Space Telescope, we put that under a bigger microscope, because it's one of those things of where you put it out there, we can't physically touch it. We're probably never going to have astronauts out there to mess with it, but you can always update the software. If that goes wrong, we're going to struggle a little bit more and have to deal with it, as opposed to if something that's a sounding rocket is launched and it goes and it's a one-time thing. We also look at the extent to which the humans depend upon that system. Again, how often do we use the system, and are we using that to save our lives? We want to look at the developmental and operational complexity. If it's a very simple operation, we will just not worry about it. And again, but if we're doing it and it's very complex, we'll have multiple levels. Also, the agency's investments in this. So essentially, we break it down into 6 levels. We have Class A, which is a human-rated space software system. That's probably the most rigorous software methodology we have. NASA spends a great deal of money and time to go through and try and remove as many bugs as possible, because we want that to be the most reliable, the most tested, and know how things are going to work out. Again, now we have Class B, non-human space-rated software systems, large-scale aeronautic vehicles. So again, we're looking at this and saying, these are, even though I may not always have these as safety critical, these are going to be big deal applications. So, and partly why I wanted to bring it up, because even though we're not counting this as a safety application, it's going to be the same aspect of this is mission critical. We're utilizing something that is costing billions of dollars. You don't want something simple or something to just easily break it. Obviously, then we have Class C, where we're getting into our mission support software. So this will be a lot of our ground testing, the systems that we use to test these flight systems. We'll also have some of our aeronautical vehicles there. That can be aircraft, jets, planes, and stuff that is owned by the FAA. And then any major engineering research facility software. Again, this could be software running the wind tunnels. This could be emulators for labs or some sort of test environment that you're going through. Again, you may not think those are safety critical, but you can run into safety critical applications because you may need to shut down hardware in a certain way. You may have crew in other aspects. Class D is our basic science and engineering design and research software. So that's probably what most people are going to be writing and sitting at their desktops and kind of doing. Then we have Class E, which is basically, again, this is your prototyping software. This is where you're just checking things out. You have a small group of people. It's not a big deal. So again, we'll have less requirements. And then our Class F, which is a general purpose computing. Again, this is our general IT software. This is what our servers will go through if you're writing a website. So again, if we're using Linux or some of these operating systems in any one of these environments, there's plus and minuses. They're Class F. Even though we may not call it safety critical, there are applications where safety is very important. You can leak a lot of information if you are doing that. I am going to note it is not uncommon for a project to contain multiple systems and subsystems having these different software classes. So again, you're going to have to look at it and say, well, our human rated aspect, we may have that, but then you may have a little thing on the side that says, okay, I'm just displaying a little bit of information. It's not going to control a system. It's not going to go through anything else. So again, we can have that kind of broken up. So to back off, and I'm sorry to get away from the template, but I've pulled this from a class that I always teach. 4 is 7150, so I wanted to kind of just reuse those slides. But give you a quick visual overview to again, kind of orient everyone. NASA has essentially 30 institutional requirements. This is chapter 2 from our 7150 or NASA procedural requirements. The OCE has their group in there. We have SNMA that goes in there. We have center and director and delegates, again, going through and kind of making through a lot of this, just trying to make sure that you guys are kind of aware. Contract officer, we have, again, the technical authority. We have the technical authority and the groups that are going on the tailoring. So again, as I mentioned earlier, we have tailoring. So even though these requirements are there, you can tailor it based on classifications and goes through the project authorities. And then we have, again, the project manager that, again, goes through and kind of works through this. This is probably not the most interesting of the slides, but again, I wanted to try and say there are institutional stuff, and you want to make sure that you have those covered. This is probably really what you want to start to look at here. Essentially, we have 100 requirements in the NPR, and we have them applicable based on our classification. We have software management. Again, how is the software managed? And that goes through everything. So again, this is going to be how the Linux Foundation itself starts to manage the software and goes through it. We have the life cycle. Again, now we're going in and say, how are you creating the software? What is your plans in going through it? You also have the lifecycle support. Are you using things like configuration management? In this, again, it's color-coded based on the chapter. In reality, we actually have 101 because one of our software engineering requirements actually has 2 shall statements in it. But for the sake of this purpose, I'm just going to call it 1 requirement. Now, I'm going to point out that there are 4 red boxes here there are 4 boxes here that have red text. That red text is there because those are the 4 that get applied in a safety critical application. And so the majority of this, we're already requiring programs and projects and developers to do and try and go through that way.
No, it's not on mute. Can you hear me now?
To start off with this, again, if you're in class A and B, and I'm saying, and I'm going to make the assumption that all these requirements and the software system has been declared safety critical. So for that aspect, all A and B, you're basically doing all 101 requirements. And that should be pretty obvious for you to say, hey, we're doing it, we want the highest level of rigor. If you're in class C, you start to drop off things like our independent verification and validation, which is a third party that's going to come in and kind of look at it. We also don't have to worry about developing and testing any procedures for any uploads of data. So again, you're going to look through that. You're not going to have to measure as much of the software volatility. And if there's any defects that got all the way through the system, we're not requiring you now to assess the process aspects. Why did those defects get in there, and how far did they come through?
Scott.
Class D, again, it can be safety critical,
can
but
you hear us?
Yes, I can.
Okay. Thanks, Vin. Scott, just to clarify, it's not the Linux Foundation that's doing things. It'll be the people participating in the project for open source. So keep that mindset in mind. Okay. Because it's not like it's not like a company you're working with here. It's like a collective.
Right.
Okay, thanks.
Right. Yeah, no problem. So again, now we have the requirements of, again, going through in Class D, again, kind of eliminating more of them. So you're going to start to go through and eliminate some of the accrediting, some of the tools, architecture, and aspects that way. Then again, if you're Class E, you're basically allowed to do a lot more of the information. So again, we're going to skip through that. Class F, again, here's our OCIO aspect. When you're looking at it, you have a bit more freedom to kind of talk about it. But again, we're starting to look at it. Most of the time, a lot of it's going to become software security. But now we're going to talk about our safety critical applications and what we mean by safety critical. Essentially, you can read all this language, but I highlighted what I found is the main aspect. And so if you're ever doing something with NASA, this is really what's going to come down to. The software is classified safety critical if the software is determined by and traceable to a hazard. So if you have some sort of hazard analysis and the software is trying to mitigate it, it's trying to control it, it's trying to take corrective action, that's really where we're going to start to look at this and say, this is what we're going to end up working on. So based on going through that, we apply several requirements. One of them is if the project has safety critical software, it needs to apply the safety standard for 8739.8, which is, again, NASA's software assurance standard. Essentially, our safety critical or our OSMA, they're going to need to confirm certain aspects, and that's one of the software requirements. I'll talk about that a little bit later, as well as, again, it's going to assess the source code to make sure it satisfies all the requirements in that same system. So again, you're going to look at that, and I'll get to that a little bit here. So actually, I guess it was the next slide. So as I'm talking about this, if we have safety critical software, we need to make sure that if you're configuring it, you're going through here, the software is initialized, and it needs to start and restart at a known safe state. That's going to be one of the main things. So you're going to have to go through, configure the Linux kernel. You're going to have to configure your system. Again, it can be a combination, which is going to open up different aspects for it. You're going to need the software to safely transition between all predefined known states. So again, as it's skipping through, we want it to be very knowledgeable. You want to have somebody know that you're skipping through all of them and going to a known state. You want to have termination performed by the software functions is performed to a known safe state. So again, as we were talking about, or as I was mentioning a little bit earlier, when you're shutting down the software, shutting down the system, make sure you turn off all of the hardware first. Make sure you've put those into a known stable state so they're not closing or they're not leaving capacitors powered up. Again, you're kind of going to skip through that. Any operator overrides of software functions require at least 2 independent actions by an operator. So that goes back to our arm and fire type stuff. You're going to start to hit those. Software is going to reject any commands received out of sequence when execution of those commands out of sequence can cause a hazard. So again, if you got the fire and then the arm, you need to reject it. You need to make sure you get the arm and then the fire. If the software, if it's safety critical, the software needs to detect any inadvertent memory modification and recovers to a known safe state. I know a lot of times we use the Linux kernel and the Linux Foundation to do that. You're going to have to enable those memory protections. Make sure that they're on and you're isolating yourself. You're trying to prove that your non-safety critical software is not affecting safety critical and vice versa. Continuing on, the software platform needs to have integrity checks on inputs and outputs to and from that software system. So even as you're kicking things through the kernel, even as you're kicking things through all your programs, you want to make sure that you have all those integrity checks. The software performs prerequisite checks prior to the execution of any safety critical software commands. So again, just making sure it's in the correct known state. And again, this kind of goes back to it, but no single software event or action is allowed to initiate an identified hazard. So again, that's putting a little bit of an onus on the software to make sure, are you able to do this? Do you have systems kind of backing up and checking? If the software responds to an off-nominal condition within the time needed to prevent a hazardous event, again, that's kind of looking at the timing. So now we're going to have to see, did you enable, for instance, the real-time kernel patch? Are you actually using a real-time patch for it and kind of go through there? You're going to need to look at it and say, hey, are you providing error handling? Are you able to accept those errors? And again, in the end, the software is going to need to place the system into a safe state. Couple of things that we get a lot of, and I want to make sure that people realize this, is when we start to go through this and require safety critical software, and you'll find this with a lot of open source systems. Not a lot of people want to go through and do the whole modified condition decision coverage aspect. But we require that because, again, we're trying to make sure that if you're running safety critical software, can you test it? Have you tested all the outcomes? Are you sure that you're not having dead code or untested code? Or if you are, understand why it is in there. So again, you're kind of skipping through and making sure that you understand, hey, is the kernel doing something you want? Do you need to compile out? Is there a reason why that's there? As well as kind of skipping through and making sure that any of your supporting software, do you understand those interactions? Basically, what we're trying to say and kind of go through this is, if you have safety critical code, have you tested it? Do you understand how it's going to act and react to any and all conditions? Similar with cyclomatic complexity, we set a general number here. I know there's a 15 in here. We've seen anything from recommendations of 20 to 10. Basically, this starts to come down to if you start to look at it and say, hey, well, we have a certain amount. Let's say it's your input routine and you're doing a bunch of case statements or whatever. Yeah, depending on how you count cyclomatic complexity, you can count that and kind of go through. So in the end, we're basically wanting you to say, understand why your software is complex or is not complex, and kind of go through there. Because as we found in studies and everything, the more simpler it is, the higher reliability. You understand what's going into it. You understand how to control it and where it's going through. That's really what we're starting to look at. So again, even if you're pulling things off the shelf, you need to kind of go through this. So again, you're going to do this. Now, I don't want you to think that you're going to have to write unit tests. So for instance, if you pull the Linux kernel, you're probably not going to have to go through and write your own test. You can if you want. I'm sure the Linux Foundation would love that, to have a nice suite of tests that you could submit back to them. But that's not really what we're getting at. But you need to kind of look at it. And again, if you're using any of the Linux systems, try and understand that this is what it goes into. So we talk about this, and now I want to say, well, why does this really apply? Why am I giving you all these implications of, hey, here's the requirements. Why did I spend such a long time talking about it? Really, we have several requirements that kind of come back in. And as most people don't realize, the project manager, one of the requirements that we have is the project manager, and that could be anyone, test the embedded off-the-shelf software in open source or reused software components to the same level required to accept the custom developed software. So essentially, we're trying to prove, do you have objective evidence that shows it works for this application? There have been times, you can look up the Ariane 5 accident, of where people said, hey, this software was good, we just reused it, and now all of a sudden there was assumption that was missing. So in that case, it was 64-bit versus a 16-bit system. You want to make sure that you know this and do it. Just because using a system like the Linux kernel, which, hey, it is great, there's been a lot of things that go into it, means that you don't know the assumptions. You don't know what somebody's writing when they thought about it. Maybe there is a flaw that they have never run into because you're using a specialized application. As I said, this does not mean that users must write all their unit tests on their own. Hopefully you can rely on some of the package creators. They have unit tests and functional tests. So again, make sure that you are not eliminating or you're able to run some of those packages through. But in the same case, if you are using your system or you're pulling some of these packages off the shelf, you need to go through a full suite to make sure that this package is responding the way you think it is in both nominal and off-nominal conditions, and kind of go through that. That's more of your that's more of your way of showing that this has been tested and gone through. We also have multiple requirements here, and again, I know, hey, we have a lot of requirement space, but some of these are from lessons learned. Again, perform software cybersecurity assessments on the software components, including anything that comes off the shelf. If you are looking at some of these things, trust me, if you start to use a well-known system, let's say people are using Linux or VxWorks or Integrity or whatever off the shelf, and people know that, people are going to start to go down and say, can we go through this? So you're going to need to want to harden your system. Are you going to provide a simple bash shell? You'd be surprised how many the IT world people are saying, well, hey, I was able to get into your Linux machine and now get a root shell and run whatever. Well, you have to prevent that. And so again, you're going to have to be aware of that. You also want to make sure that you establish, capture, record, and approve any of the software requirements. So again, as you're going through, you need to write the requirements for what is this off-the-shelf component doing, whether it be the Linux kernel, whether it not be. Just make sure that you understand this is what it's being used for, and you want to test those to make sure, hey, is it maintaining? Because there could be some updates, there could be some decision where it's adding functionality that you don't need or don't care about. Again, testing the requirements against its practices. Again, a best practice, again, we will have a formal software test campaign planned, witnessed, conducted by an independent organization outside of your development team. So again, you're looking at it. I'm not claiming that you have to go in and do all of the testing for the Linux kernel, but at that point, you need to make sure that somebody's there and somebody's at least understanding, hey, this is the requirements and the needs you have of the Linux kernel or this Linux package or whatever, maybe it's BSD, and use it from that way and kind of go through that. You also need to use validated and accredited software models, simulations, and analysis tools. Some of these systems may not be set up. If you're using a non-real-time Linux system in a real-time environment, hey, that is probably not valid for the system you're using. Yes, it may work 90% of the time, but that time where you need that determinism or need that restriction, you want to make sure it's there. If you are starting to go in, this gets a little bit outside because, again, we're not looking at what's the order of approximation of any of your simulations. So that's where NASA has NASA Standard 7009, where you're capturing all the assumptions, you're capturing that information so you can communicate it. And again, understanding what goes into it and what each package is giving you. Testing requirements as well. Again, you want to verify that the code's coverage is measured by analysis, and again, look through all of the execution of the test. You want to make sure that all lines are hit and you are understanding why you're getting there and is it doing what you want it to do. If you cannot hit someplace, because again, I know as a software developer myself, I may write multiple packages, and one package has a defense against like a null pointer. Well, if I'm reusing that in a system where I'm already defending against that and didn't realize it, yes, I may not be able to hit that little bit of code, but I can explain why. And when I'm breaking it down, I can show that I can hit it in certain situations. You're also going to need to conduct any software regression tests. So again, don't just take whatever package is put up there or whatever updates. Understand, does it just pull through and are you sure it's going to work for everything? Some of these packages or some of these updates have broken things and they may not realize it. And that's including a security vulnerability. So as I said, pay attention and make sure that you're not just saying, hey, well, our IT people are saying pull it off the shelf and kind of go up through there. You also want to, or you're actually required to verify through tests the software requirements that trace to a hazardous event, cause, or mitigation technique. So as that's kind of basically illustrating, you want to make sure that if you have any hazards, you're not just saying, well, I can look at it and say it. We're basically requiring you make a test to do that. A test is always going to prove better that it's always working. And that's going to make sure that, for instance, let's say the compiler has a bug in it, or maybe you're enabling something through your tool set. All of that is working because you're actually seeing what the fundamental or the final code is generating and what it's doing. Not, well, it looks correct in C or it looks correct in Python. Sorry, kind of dirty saying that, but it looks correct there, but as you're going through, you actually know what it has, because we have found bugs in systems, in compilers, in tool suites to kind of generate all of the metadata and everything before. And I'm sure a lot of you have probably seen that as well. Hopefully we're getting these things down, but hey, everyone's imperfect. Everyone's going to make a mistake at some point in time. The last aspect, or the one I have on this, is any acceptance tests for loaded or uplinked data, rules, and code that affects the software and the software system. Those all need to be tested and validated and verified. Again, a lot of us, we're starting to go more towards data-driven systems. So as you're doing some of these offline configurations, you can test the code, but now, hey, what about all the data that you're putting into it? You do not want to get stuck in a race condition. You do not want to get stuck someplace where something comes up and you just didn't realize it. Again, a lot of this seems like it's straightforward, but there are nuances that go into it. And you're going to need to write a package that kind of goes through and says, this is all of what we've done for this. So to that end, what else is needed? Again, I've been talking about this. We've kind of been going through and saying, hey, provide evidence of this, provide evidence of that. There are the security things. I know my friend Josh Craigie is going to talk later on today about some of the security aspects of some of these systems, because again, security is always going to come into it. We still have to figure out policies. What about having a badge reader on an airlock? Do we really want to do that? That's always been an odd question, because you don't want to sit there and have someone say, well, I dropped my badge, and so now I can't get into the airlock for whatever reason. So you're going to have to step through that. But some of the little things that I wanted to kind of point out is, in any one of these systems, you're going to need to do and kind of prove that your system is very deterministic. This is going to be what struggles when people start to get to some of the AI type topics, because again, a lot of those will have random generation inside of that, or they're using statistical means. So if Linux is an operating system and it's running on unknown hardware, again, Linux may be great, but your hardware can determine some of that determinism. It's going to vary. Maybe you just don't have enough memory for it. You're going to have the system configured to provide information or ways for users to determine a guaranteed response time, whether that be using kernel modifications, whether that be using the real-time patch. There are real-time Linux systems out there that you can buy. But again, now you're going to have to understand, well, what is the package and what is response time? Because some user or some package maintainers may say, well, we guarantee to millisecond accuracy. Well, okay, that's the response time, but maybe you need microsecond accuracy and microsecond response time. So again, just because you can pull it off and people say it's real time, make sure you have that and understand. Again, and you can kind of look at this, the memory, schedule, and other resource protections. Make sure you're enabling the correct response and isolation on these Linux systems. Because again, Linux can allow you to do things. There was just recently the article of Linus Torvalds kind of making his comments about Docker and how they're going through there. It's doing isolation in a different way. And so you can still kind of break through. So again, if you're using it, you need to enable it, because the off-the-shelf version of Linux doesn't always let you do it. That's one of the strengths of Linux, is to be able to compare and enable and customize a lot of these things. That's why I love these. So again, you're going to have to do it. You're also going to need to do things like prevent inadvertent memory modifications or any cache protection, because by default, they may or may not do it. I pulled a couple packages that I used to use or have used. There's mprotect. You can go and use that command. There's CPU set. Again, that's making sure that your system is more deterministic, or you're locking a system to a core so you know you're not getting those cache hits. Maybe it's IRQ affinity, so you're making sure that your processor isn't having to service an interrupt request. But in the end, you want your system to be very robust. That's really what we're going for, because in a lot of these safety critical applications, it can't be like, hey, it crashes, my program goes down, and then, hey, no big deal. When you're thinking about it in some of these more safety applications, or as you kind of go up. I took this out of the presentation because I was going back and forth on it, but now I want to talk about it a little bit. I mean, think about it. If you're using Linux in a car on the earth, you can pull the car off to the side without a problem, especially if there's a software problem. In an aircraft, if you have a problem, there's not as much you can do. Your gravity's going to bring you down. So at some point, now, yes, you're not going to drop like a rock. Those the aircraft are designed to kind of glide and at least come down. But again, you're going to have gravity and you're going to have a different thing. You don't know if there's a landing spot for you. In space, you have nothing else. You're on whatever orbital trajectory. If that system crashes, the astronauts just can't go outside and wait for help. How much time and effort does it get to take somewhere? Again, maybe you're on a trajectory, you only have a certain amount of fuel or oxygen. So again, that's where we want it to be robust and say, can we go through all this? That's kind of the aspect that you're looking at. How can you make sure that you have everything robust and gone through there? Some of the support-wise, for these safety applications, the teams are often going to need and want support with defined response times. So you may have to look into paying for something and kind of looking and saying, well, we just can't get a package off of Stack Overflow or just can't pull down from GNU and go through that. Again, and to talk about it, you could say Red Hat. Red Hat has built a model on providing support. So again, sometimes these open source problems, if there's a bug or a feature that you need, you're going to look to how can you get this added. Some places will say, hey, we'll take money to do it and patch that bug for you, provide support. So again, you're going to have to look at that. There are models for some of these vendors in place, like I mentioned. And then again, you want to trade off with cost. Part of the fun of having this is being able to use it open source in a no-cost solution. Or, hey, we're all used to being able to write a Linux package and kind of go through there, do a kernel module ourselves. You want to make sure that you're not interfering or doing anything. And, hey, you can do it no cost or even a low-cost option. So, again, now as you're using this system, you're going to have to go through some of these steps and understand what is it that you're enabling and what are the requirements that go through it. So, to that end, I know I basically went up against my time. I want to know, are there questions that people had?
Yep, we've got some here in the room.
So on that list of 100 or 101 requirements, are there any that are known to be incompatible with open source software methodologies?
There are none on there that are incompatible with open source software. Again, now you're going to have to look at how much does that person spend the time to go through and do some of it. For instance, some people may not want to write the unit test. They may not want to write requirements down. So again, that's going to maybe force you to do more testing on your own or try and figure out what assumptions went into something.
Well, I guess one of the things that I thought I saw in an ESA safety requirement was that the requirement was written before the code. And that's not what happens in open source software, right? So you don't actually write the code to the requirement.
At the high level, you would. At the lower levels,
well,
you're
not
reusing things, so that's our problem. Yeah.
Well, so at that point, yes. I mean, you're thinking of more of a waterfall methodology, and you can go through that. But at the same time, think about, like, let's take OpenSSH or OpenSSL. They have requirements that they may not write down, but they're writing to say, this is a security that we're going to provide. These are functionalities. As you, as a project or a person, what are the requirements that you want that software to do? And does that software do that? Because it may meet 10 of your requirements. Maybe it's meeting 90% of your requirements, but it's not doing one part of it. So yes, you're going to have some aspects of that to say, well, what are its specific requirements? But again, in theory, the teams or the people that are writing some of these, they should have a reason for why they're doing each one. You may be able to look into their kind of repositories, but it's not all of a write every requirement first and then start writing code. You can iterate through, but even if you're using the package, what is the requirements you have on those packages? Are you meeting all the needs for that package?
Yeah, Tim, how is that different than writing requirements? Like if you're writing a driver, open source driver, that the requirements are the driver itself too.
Well, no, but like some of
Requirements have to be testable.
yeah, some of the ESA requirements aren't that, the requirement comes first. And then the code. And you can't do that with open, source, right? So,
But you can't talk about that.
well, okay, so.
Requirements can be before the code, design maybe not. The design is, well, let's. We got a session just on that.
So Scott, from NASA's perspective, is it a requirement for the system that has to be defined first? Not a requirement on necessarily the subsystem or the dependent software.
That, right there, that's the right, yes.
So, sorry, were you able to hear me? No, maybe not. Yeah.
Well,
You can move forward.
I see Yvonne on Zoom raised his hand.
Sorry, I guess you guys weren't able to hear us in the back of the room. If you could. Please.
Hello. Can you guys hear me in the room?
Yes.
Do you hear us?
So with respect to that question that you just mentioned about requirements that are incompatible, even though in theory they may not be, there are requirements that, as you said, are kind of say unfriendly to the normal open source process. And in that case, you would have two ways to go about it. One of them is that you could potentially tailor the requirement. The tailoring has to be approved, but you could request it. And then the other thing that we have done, and I'll talk about this later during the Space Rust talk, is we've come up with a process that tries to be very, very lightweight, that delivers the majority of meeting some of those requirements without getting too much in the way of the open source process. So it's something as simple as say, in all of your commits, tag the issue that you're actually trying to address and don't address multiple issues in the same commit. And that kind of forces you to go to the issues, and we use the issues as change requests. And that forces the person who assigns the issue to say, why is this issue being worked on? Is this because a requirement was not being met? Is it because there's a new requirement? Is it because there's a new need? We don't use the formal language of requirements in the sense that we don't call them requirements, but that's the idea. Like, are we trying to accomplish something new? How does this align with our plans? So we've kind of met somewhere in the middle, and it seems that it's possible. Yeah. Over.
There's no question in the room. Is it the laptop microphone? Which microphone?
All right, Scott, are you able to hear me now? Sorry, I'll back up so you don't have to see my chest.
Yeah, go ahead. I think you heard.
Okay, so the question is it that the system has to have a requirement before you begin development, or is it that at the subsystem level? That is, if I define an overall system requirement, is it mandatory that any component that I bring in that may or may not be open source also have their requirements defined ahead of time, or is it really just at that systems level? You're muted.
You're muted.
Still muted. Scott, you're muted.
No, he's not muted.
Oh, he said he's double muted. Sorry, Scott, do you have a hardware mute maybe on your microphone? We've lost you.
Maine, can you hear Scott?
I cannot either.
Yeah.
Hmm. No, we still can't hear you.
All right. Well, we're also running out of time, so we're gonna have to
Yeah.
skip this one.
I
Okay,
am
well,
gonna stop
Thank
the
you, Scott.
recording.
Can you
Thank
hear
you,
me
Scott.
now?
Is there?
We can hear you now.
Yeah. And then we can be